Hello everyone, I'm Ümit Alkuş. In this video, we will solve one problem in Chapter 9. The figure shows a collision between two billiard balls of the same mass. Ball 2 is initially at rest. Find the angle theta. Assume that the collision is elastic and that there is no friction on the pool. Because this is an elastic collision, total kinetic energy of the system is conserved. Namely, initial kinetic energy of ball 1 plus initial kinetic energy of ball 2 equals final kinetic energy of ball 1 plus final kinetic energy of ball 2. Initial kinetic energy of ball 1 is 1/2 m times v1I squared, where v1I is the initial speed of ball 1. Because ball 2 is initially at rest, then its kinetic energy is initially 0. Final kinetic energy of ball 1 is 1/2 m times v1F squared, where v1F is the final speed of ball 1. And final kinetic energy of ball 2 is 1/2 m times v2F squared, where v2F is the final speed of ball 2. The terms 1/2 m are cancelled. As a result, we obtain the relation between the initial and final speeds as v1I squared equals v1F squared plus v2F squared. In all collisions, total linear momentum of the system is conserved. Namely, initial total momentum of the system equals final total momentum of the system. This equality of vectors states that their x components are equal, also their y components are equal individually. Let us decompose the final velocities onto x and y components as follows. The x component of the initial momentum is only due to ball 1, because ball 2 is initially at rest. Then we write m times v1I for the x component of the initial total momentum. After the collision, we have m times v1F times cosine theta for the x component of the final momentum of ball 1. Plus m times v2F times cosine 35 degrees, which is the x component of the final momentum of ball 2. Here, m's are cancelled, so we obtain v1I equals v1F times cosine theta plus v2F times cosine 35 degrees. The y component of the initial total momentum is 0 because there is no motion along the y-axis before the collision. The y component of the final momentum of ball 1 is negative m times v1F times sine theta if we take the negative y direction as negative and the positive y direction as positive. And the y component of the final momentum of ball 2 is m times v2F times sine 35 degrees because it is in the positive y direction. Again, m's are cancelled. 0 equals negative v1F times sine theta plus v2F times sine 35 degrees. If we square both sides of equation 2, we obtain and if we square equation 3, we obtain if we add these two equations side by side, we get cosine theta squared plus sine theta squared is 1. Also, cosine 35 degrees squared plus sine 35 degrees squared is 1. For the last term, if we use the trigonometric identities, we get cosine theta plus 35 degrees. Finally, we get this result. If we compare this equation with equation 1, we say that this term is 0. Because V1f and V2f cannot be 0, therefore the cosine term becomes 0. This means that the angle is 90 degrees. As a result, theta is obtained by 55 degrees. An easy but somewhat advanced solution is the following. If we use the conservation of total momentum, since initial momentum of ball 2 is 0, we obtain m times v1i equals m times v1f plus m times v2f. The masses are cancelled, so we get the vectorial relation as follows. If we square both sides with dot product, and remembering that dot product of a vector with itself gives its magnitude squared, so we obtain v1i squared on the left hand side. On the right hand side, we use the distribution law of dot product, namely v1f dot v1f, which gives v1f squared, plus v2f dot v2f, which gives v2f squared, plus v1f dot v2f, plus v2f dot v1f. Since dot product of any two vectors is just a scalar, change in the order of the dot product does not change the result. Therefore, we write v2f dot v1f as v1f dot v2f. Then we obtain 2 times v1f dot v2f. Remember from the first way that kinetic energy conservation gave us v1i squared equals v1f squared plus v2f squared. If we insert this result into the equation, we obtain v1i squared plus 2 times v1f dot v2f. v1i's are cancelled, and from the definition of dot product, we have v1f times v2f times cosine theta plus 35 degrees. Finally, we get this result. v1f and v2f cannot be 0, so the cosine term is 0. Cosine 90 degrees is 0, so theta plus 35 degrees is 90 degrees, from which we get theta as 55 degrees. As you see, this method also gives the correct result. Okay, this is the end of the discussion of this problem. Thank you for your attention. See you in the next video.